system, if I wanted to validate the proposed approach within the railway system, I would need to replicate a test matrix with different speeds and different loads. That was not possible. After a few tests, one of the railway drive station failed. But even if I was able to complete such a test, I would still need a data set representing different faults. This is really impractical, given the huge size of the industrial drive station. They would need journeymen to disassemble. It was not impractical. But the good news is that for the majority of condition monitoring research, it's really, the actual system is rarely used for the development of condition monitoring solution. Mostly we either use, or we used a machinery fault simulator representing a smaller scale version of the machine of interest that is highly accessible for fault seeding, and it can be continuously operated. What you see here is a gearbox vibration for a wind turbine simulator, and it's been used by the round-robin study issued by the United States Energy Department. A huge study involved 16 industrial giants in condition monitoring and wind turbine manufacturers. The other one you see here is rotor drive assembly used at the University of North Carolina. It represents the rotor drive train for an Apache attack helicopter, and it's used for developing a condition monitoring solution for helicopters, drivetrains. The tabletop simulator that I used served its purpose, but it couldn't be used any further due to its limited loading capabilities. It couldn't allow for continuous loading, given that each load was I had to add loads, so I didn't have that continuous profiling. And it's oversimplified. It lacks an integral transmission system, and even if it had a transmission system, I would need two transmission systems to look into the parallel fault detection. So to address the need for a new machinery fault simulator for a year, I designed, developed, and fabricated a new machinery mechatronics test bench with the following design specification. It should replicate parallel system arrangement, have identical subsystems that are continuously simulated, representing different duty cycles that are realistic in speed and loading. Its modular design can be modified quickly. It's fully instrumented and fully accessible. So this is the machine that you can see here. So it's two identical drive stations. Each drive station has a transmission system driving to a hydraulic pump. And you can see that each drive station is powered by identical 10 horsepower motor through a custom gearbox that I made here that allow for easy fault seeding. And you can see that each drive station, each output for each gearbox carries a crank pulley driving a serpentine drive system with active tensioner that allow fault detection, like we can do in research in fault detection of serpentine systems. And two drive stations are loaded using hydraulic pumps that are fully serviceable, allowing for future research in hydraulic fault simulation. The flow from the load pumps is directed into a loading circuit that I made, where you have a proportional valve controlling the pressure being sensed by those two pumps and transmitted as reaction torque for the two drive stations. So the hydraulic subsystem represented a critical component who underwent design, prototyping, and validation. So the circuit has check valves, safety valves, and the proportional pressure relief valves, and two pumps. And then I simulated the circuit using fluid sim. Before actually making the circuit, I prototyped it on hydraulic simulator. And then I made the final circuit with two things in mind. It has to be safe. You can see I'm using GIC fittings to prevent overpressurization, and it's compact by using swivel joints. And before actually putting it into the machine, I tested it at a friend's local shop, the physical circuit itself. So it's a mechatronic test bench that is fully instrumented. So you have accelerometers for the motors, gears, the gearbox, and the pump, the gearbox and the idlers. I have Rogowski coils to measure the current for the motors. I have high resolution encoder for speed. And I have a pressure sensor for circuit pressure. And then the control to simulate different speed and loading, the motor inverter, and this is the current, proportional current driver for the solenoid valves. and all control was done in FPGA in real time using LabVIEW. So the fabrication, just the fabrication shows you all the machining steps that I had to complete in the machine shop to make the mechanical structure itself. So equal effort has been put into designing the hydraulic system and developing it and actually making it and putting the whole system together. It took me over a year, and it was a major part of my research effort, but it's, I believe it's a very important research tool for the development of condition monitoring solution for non-stationary operation with special focus on parallel systems. So baseline data collection was done to ensure the performance of the new simulator. So for the sake of the presentation, I will look at instrumenting the output flange for the gearbox, the idler, and the motors. So you can see here the spectrum for the outboard bearing flanges for the gearbox. Given that both gearboxes are identically constructed and operating against the same duty cycle, they have the same frequency components, and even the amplitude level, they have the same scale, the amplitude is fairly similar. It's the same situation for the idlers, the vibration signals are similar, and the spectrum also have the same spectrum components. It's the same thing for the motors. You can see from this, however, you can see from the spectrogram that the right motor is a bit noisier, so you can see that frequency grouping, but still you have the main frequency components available. It's a different situation for the input bearing of the gearbox, where you see that the left gearbox is significantly noisier, a bit noisier. You can see that in the frequency domain, and you can see it in the time domain. This is the left gearbox line waveform. And if we look into the variable duty operation of the new machine, we can simulate variable operation. So we look into speed ramping, hold speed and load ramping, hold speed and load down, speed down. If we see it in this, again, it's the same input bearing, noisy input bearing. We see the spectrograms, we can see that we have the same components, and they are shifting with frequency at the same time, but the left gearbox is considerably noisier than the right gearbox. So the final assessment is that the amplitudes of the time waveforms are fairly similar, and they change simultaneously with duty cycle. The spectrum had the same components. The frequency similarity in amplitude varied between very similar maybe for the idlers and the output gearbox flange to the really dissimilar for the input gearbox flange. So the time I spent in developing the machine, really due to the context of a master's thesis and time restraints, I didn't really have enough time to fully validate the proposed solution using the new machinery fault simulator, fortunately. But I had enough time to look into preliminary testing, which I will present now. I did preliminary testing for idlers and gears, but for the presentation I will only look into the idlers. So we'll be looking into healthy, and faulted and healthy. So I replicated the test matrix at different motor loads and different motor speeds. First thing you would notice is that for the healthy we have non-zero discrepancy metric. This was expected. The new machinery fault simulator is significantly complex compared to the other tabletop simulator, and it had several subsystems within it which add to the stochasticity of the signal. And to see the changes with speed and duty, we can look into the statistics of the correlation scores. So the correlation scores, over the speed, they ranged from 3.88 to something like 6.49. Max to 9.54. So they're within a same range, and they have a similar mode and similar standard deviation. Even I changed the speed from 500 to 900, and the speed changed the load from 5% to 35%. To see the effect of a fault, and to see, before that, to see how it's insensitive to speed and load variation, the blue one represents 500 at 5% load, and the red one represents 700 RPM at 35% load. And again, this is the distribution of the correlation scores. And you can see that it is rather shifted to the 10. So if you look here into when I induce a fault, you can see that the presence of a fault has increased the discrepancy metric from 18 to 315. That's like 10 to 20 volts increase. So you can see how a fault can really affect the discrepancy metric. So the separation, you can see here that at the same speed, the dotted one is healthy at 5% load, but the blue one, the black one is 500 RPM at the 5% load. So it's the same loading cycle, but now it is a faulted component. So you can see that the faulted one is pulled down towards zero, and the blue one and the healthy one is pulled up. And you can see any time the discrepancy score is below 5, the correlation score is below 5, we have a discrepancy hit. So for the healthy one, we have few discrepancy hits, but for the faulted one, you can see that most of the correlation scores are actually below 5, and that's why we have that really high discrepancy score. So what I'm proposing here is that we can modify existing classical alarm-based system such that instead of looking into RMS trending, we could look into the trending of the correlation scores. So again, this data was generated using the new volt simulator. So it's an RMS for healthy systems, but at 500 RPM, 5% load. So you can see it's over here. Just the increase in load and speed increase the RMS over here. Again, perceived as a fault by normal, by commercially available fault simulators. However, that same increase in speed and load didn't really affect the correlation score, but still has the same same mod and similar variance as we seen in the previous table. But the presence of a fault, you can see the separation due to the presence of a fault as we previously seen. So the benefits of this proposed approach is that it requires no pre-labeled data or mathematical models. No information is needed regarding the duty cycle, so you don't need torque sensors or speed sensors. It relies entirely on well-established classical correlation analysis techniques, and it's computationally inexpensive, as you've seen. So the limitations, one might assume that it requires double the instrumentation because you have to instrument 2 drive stations, but again, you're instrumenting only acceleration. So from a cost analysis, you can see that the added cost of an extra accelerometer is significantly less than having to instrument for torque or speed, which you would require for mode classification for the pattern recognition approach. You're processing double the data, yes, but again, the processing is simple compared to pattern recognition approach, and as can be done in real time. But it is really applicable only to parallel machinery, since we need 2 identically loaded systems to generate the residual. So the conclusion is that the concept overall is promising. It's been tested on the tabletop fault simulator, and the promising results allowed us to do a field data collection, where we realized we needed a better fault simulator that has better capabilities, and that's what we did. And it would merits future work I will discuss in a second. The machine itself is a valuable research tool for future research. So the future will include modification to the simulator, add torque sensors, and maybe the gearbox has to be fixed. All this is being done right now. The new gearbox is being made, and the torque sensors have been purchased. Extensive data collection is needed. We already did another 60 or 68 different tests for the idler bearings. Prolonged data collection phase at Railware. If we have a strong case, we can approach Railware and ask them to allow us to fault the drive stations. Finally, we need to investigate its applicability for pumping station. We can investigate hydraulic pump failures, and this opens up a new prospect for our application. So I'd really like to thank my research leader, Dr. Mark Stilmes, for all his help, the Center of Excellence Mining Innovation for the generous funding, and Mr. Anna Hickerman, thank you. Railway Technologies for in-kind contributions and field testing, and Mr. Greg Blackinen from the engineering department. So this concludes my presentation, and I'd like to open the floor for any questions.
Thank you very much, Mohammed, for this clear presentation. So, Mohammed will be accepting questions from the audience. The committee should reserve the questions for the private meeting after we're done here.
Well, I'll ask a question.
Sure.
Since you're doing things in parallel, does the life of the piece of equipment matter? So if you have a bearing that you replace in year one, and you keep the other bearing going past that, the correlation still has to be the same one-to-one in order to get your form factor to be the same? Or will be a slight variation because one bearing is slightly
Yeah, it would be expected that there would be slight variation that is due to wear. So what we're assuming here is that the maintenance is only done for those drive stations. The both drive station has been installed at the same time. It is a possible situation that the condition monitoring would predict a failure in one of the bearing for one drive station, and then you would have to change that drive station bearing. So I assume that that would change the correlation, but again, we're looking into the trending of the correlation score. So again, a new fault which shows up as a significant, assuming that it is a significant fault, it would show up as a significant change in the correlation score. But of course, the effect of wear is something that another limitation for this approach is that it doesn't put in it doesn't really pay much attention to the fact that even if they're the same components, they might experience different wear levels. This is a very good valid point. Yes?
Sure. Has a little bit less to do with something maybe you thought of about the future application of putting this algorithm to the test. So if you're deciding on the health status of the two similar operating subsystems, do you foresee a method of using this technique to determine where the failure has occurred? If you're just comparing the two discrepancies, is it possible? Yeah, is that something you've thought about?
Well, what I'm thinking about as a framework is that so it's as simple as possible. We are comparing those signals, and then there's a discrepancy. So one of the drive station has faulted, and then you would assume that the one that's faulted has its vibration signal has changed. So in the framework, I'll be logging the vibration time history for both drive stations. So the one that has faulted would have its vibration time history has changed with respect to what's been usually seen before. And then through frequency analysis, given that you're looking into vibration monitoring, it's assumed that different components have different frequency signatures, vibration signatures, and then you can pinpoint where the fault is. So by comparing it to the previous history points.
So the proposed algorithm is more, tells you if there is something that has occurred, some novelty, and then
further investigation is required. So again, like in the drive station, you have all those numerous drive stations driving the whole system, and some of them are underground in close quarter drifts. So like being able to continuously monitor the drive station such that if one of the drive stations start misbehaving, this is a really advantageous information for like the maintenance department. And then they would start looking into which machine is actually faulted.
If nobody else has another question, I'll follow up with one other quickly. The possibility, when you were testing, and I know this might be, you haven't had lots of time to go through all the data from all the testing you've done, but I think it would be logical to assume that if you're doing discrepancy scores based on, if you have 3 or 4 accelerometers on each subsystem like you were during testing, that you would have a higher discrepancy at a certain location between 2 gearbox accelerometers or 2 motor accelerometers, that you would be able to pinpoint where you would expect that the higher discrepancy would relate to where the failure occurred in the subsystem.
The discrepancy is more of a measure of the similarity, so it doesn't really say which one is failed.
Right, but you would know which component on which component is leading to the.
Yeah, oh, okay, so now I understand what you're mentioning. So you're saying which component of the drive station, whether it's the motor or the gearbox.
Right, so did you know, I don't know if you did any investigation as to.
I misunderstood the question. Initially, I thought you were asking like which, maybe like the gear or the bearing within the gearbox itself. Right? If it's what you're saying, right?
Well, this is the second part.
This is the second part. This is a new part. Okay. So what I would say is that yes, because you're going into the if you have the chance to put in more accelerometers, then you can instrument the gearboxes, you can instrument the motors, and you would, of course, a fault in the motor will even change the signature for the gearboxes as it resonate back, but it would be more clearly seen at the motor source point itself through the accelerometers attached to the motor.
Right.
That's my understanding.
So the potential of this would be, depending on how much of instrumentation.
How much of your instrumentation you can
you'd be able to find which component.
Yeah.
You might not know until you do further investigation which subsystem, which side is failed, but you would know which component.
Which component is exactly, which allows them to like really pinpoint where the fault is going. Yes.
One more question?
Yes.
So the work that you were doing is being done on independent pieces of equipment, right? So your pumps are independent, your gearboxes are independent?
Yeah.
So can you use the same technique on basically monitoring the inboard and the outboard bearing of the gearbox?
Yeah.
Where you have a single shaft going through?
Yeah. This is something that's been looked by previous PhD student, Dr. Marcus, and that he was looking in the correlation, as you're saying exactly, he's looking at the correlation between the two maybe like bearings for a gearbox, and if that correlation has changed, but he was using a pattern recognition approach. But it is, so this is another application you can look into. If you use the correlation coefficient or like the correlation scheme itself for a single system, by comparing the correlation between the different components within the system, if it's if a change in the state, health state occurs, then that correlation will be affected. Yes.
Okay, thank you very much for the audience, for the questions, and thanks, Mohammed, again. So now we will go to the private meeting between the committee and yourself. Marcus, the meeting is going to take place here or in the room?
Why not here? Because he's got the presentation up here.
So here, yeah.
I think it'll probably tie right the whole time, I'd say.
Yeah. You actually ordered this up, setup. Please test that. So we've already got those, we've already received the.
Sorry, Marcus, I called you Tom earlier.
Yeah, so that was
My brain is marked by Tom Thomas, physicist.
Yeah.
I read his article.
I didn't even notice. Yeah. I'm used to it at home. Yeah, my uncle's a prof at master. Physics. Do you know him at all?
I attend seminars by him, like at conferences and so on. But we do not. I read his papers.
He's 80. He would be 83 right now.
still working.
Still has a discovery grant. Yeah, he retired maybe 15 years ago, but he still has a group and works, so
Yeah.
it won't give up.
Yeah, he does great. He does a great job. Yeah. Okay, so let's start. The way it works, like for our defenses, is that we go around like person of the committee asks a question and then we go around again. So how about you? You start?
Sure. I think you've done a good job.
Thank you.
Maybe my first question is related to your presentation.
Yes.
Could you move to slide 4, please? Yes. Here, for third.
I'm so sorry.
Yeah.
That's I'm sure.
You stated that vibration monitoring is ideal for rotating equipment.
Yes.
Compared with some other information carrier related monitoring, such as thermal,
Yeah.
such as current. Could you clarify this issue? Why vibration monitoring is better, is more
Yes.
ideal in this case?
So as you say, sir is saying, the condition monitoring involves the monitoring of the machine, and you can monitor different parameters. And for rotating machinery, vibration, again, we have to differentiate between high-speed rotating machinery, such as maybe wind turbines, where we're looking at like flexible shaft that has a rotor on it. Then they use proximity probes. But for applications that we're interested in mining and rotating machinery, such as motors, gearbox, where vibration is, first of all, its monitoring is non-invasive. So you can monitor machinery by lubricant analysis, such that if the gears are starting to wear out, you can see chips. But of course, it means that you have to do periodic testing of the lubricant and it's sent to a lab. So it is like, it's really like it takes time. Vibration is highly accessible. You can just use a piezoelectric accelerometer and just mount it, and then it's done. It is, again, it's inexpensive compared to lubricant analysis, and you don't maybe there's like thermal imaging. You can have a thermal camera, but again, cost analysis, like the cost of a vibration sensor is much less. And the thing is that the vibration sensor can be permanently installed in the machine. Some manufacturers actually design the machine such as it has permanently installed accelerometers, and which is like compared to thermal imaging, you won't have that thermal camera all the time over there. So we said that it's inexpensive compared to other solutions. It is highly accessible, and it is non-invasive. You are not actually interacting with the machine, compared maybe some application require torque monitoring, so you're looking into the changes in the torque. But then you have to install a torque sensor, which is like couples to the two different motors, introducing this alignment. This is completely non-invasive. And finally, it is coupled to the inner working of the machine. Each component in the machine, like it's rotating, it's operating at a certain speed. Given its kinematics, it generates vibration signature. Bearings generate vibration signal that is drastically different from gears. So bearings have cyclostationary signal. Gears have determinate signals that are phase locked to the speed. So through the vibration monitoring, you can actually pinpoint where your fault is. So if, as like Craig was asking, and that's what's done in for the stationary condition monitoring, which is well established, is like they look at the FFT and they can determine you have frequency component representing the bearings, you have frequency component representing the shaft harmonics, the gearbox side planes. So it allows you to pinpoint the source. It is the first thing that starts changing. So like from that graph, you can see that it changes way before you start hearing noise or you see change in the system heat. Heat is actually like something has actually started wearing out. So it's inexpensive, it is highly accessible, it is non-invasive, it allows you for fault diagnostics, and it is directly coupled to the mechanical state, so it allows